Good morning, and welcome to today's Military and Aerospace Electronics webcast. Our topic today is developing high-rel brushless motor controllers for space applications, sponsored by Virago Technologies. I'm John Keller, Chief Editor of Military and Aerospace Electronics. Today, we'll be talking about brushless motor controllers with experts from Virago and their customer, FlightWorks Incorporated. Specifically, we'll learn in detail how FlightWorks approached the challenge of developing high reliability brushless motor controllers for specialized space missions and ultimately leveraged microcontrollers to build a highly reliable, radiation tolerant, flexible solution to their customers' space missions. First, let me explain how you can participate in today's presentation. First, if you have any technical difficulties during today's session, simply type your issue into the Ask a Question box and a member of our team will assist you. You also can click on the question mark help button in the upper right corner of the screen. Additionally, we welcome your questions during today's event. We'll answer as many questions as we can during the Q&A session following the main presentation, but please feel free to send in your question at any time. To do so, simply type your question into the Ask a Question box and click on the Send button. Also, please be aware that today's session is being recorded and will be available on the Military and Aerospace Electronics website, which is www.militaryaerospace.com. That'll be available within the next week. You'll be notified by email when the archive is available. Now I'd like to welcome our speakers for today. From FlightWorks, we have Eric Besnard, President and CEO, and James Robertson, Senior Avionics Development Engineer. From Virago, we're joined by Danny Miller, Senior Applications Engineer. It's great to have you all with us today. Would you please take a moment to introduce yourselves to the audience and share a bit about your background? James, would you like to go first?
Yes, hello. I've been an engineer designing aerospace electronics for almost 20 years, focusing on motor control for the last 10 years. My projects include working on flight control actuators for tilt-rotor aircraft. This application demanded high performance as well as redundancy to meet a very high reliability requirement. To handle this unique need, I designed redundant servo motor control electronics and a redundant brushless motor. At Vector Launch, a small-sat launch company, I designed motor control power electronics for applications on the launch vehicle, including for TVC actuators and pumps.
Okay, Danny, would you like to introduce yourself?
Yeah, my name is Danny Miller with Virago Technologies. I'm a senior applications engineer. I've worked here with board level work and the power supplies and the applications, how to apply it, the microcontroller code, and helped with radiation testing and our test benches.
Okay. Also on the line, we have Jim Williams, Principal Engineer from Virago. Jim's here to check on any questions that come through in the chat, and he will pass along any questions to the moderators for the Q&A session at the end of the discussion. So if you have a question during the discussion, go ahead and put it into the Ask a Question box, and Jim will be able to help make sure we get those addressed. So let's dive right in. I'll kick things off with you, Eric. Can you start by giving us a bit of background about how FlightWorks got involved with motor controls for space and the specific solutions you've developed to support the specialized needs of space missions?
Yes, good morning, and thank you for having us. As you said earlier, I'm Eric Besnard, President and CEO of FlightWorks. And for about 20 years, we've been developing and manufacturing and selling miniature fluid components and small systems for a variety of applications in aerospace and others. And that includes very small fuel pumps for unmanned aerial vehicles in aerospace, space propulsion, and medical devices for things like implants. And the key behind all of those is high quality and reliability. And about 10 years ago, we introduced this idea for using those pumps for space propulsion applications. And the key element there was to be able to use those for obviously very high reliability applications. And customers were coming to us and asking, well, you've got the pump, and how am I going to drive it? And the reason for this is, for reliability, we went with brushless motors instead of using conventional brush motors. And to be able to do that, you need some kinds of electronics that are not typically found on what spacecraft bus operators develop. And so specifically the motor commutation. And that's what led us to do that. We got enough inquiries that we said, okay, fine, we'll actually dive into that and engaged James to lead that effort with a team of developers here, and which led to the products that we're going to talk about and how it's different from some of the things that you can find on your, what's driving your electric bike and the fact that we're dealing with space environment. So that's what led to that.
Okay. I've got a question. What does radiation tolerance and radiation harden actually mean, and why is it so important? Danny, what do you think?
Well, terrestrial applications deal with very low levels of radiation. The radioisotopes do exist in the regular room. If you put a Geiger counter on the table, you will eventually hear a few clicks per minute. They are not the type of thing that would normally cause any problem with it. And what we call commercial off-the-shelf parts, COTS, don't really have any need to deal with that. Once we go into space and we leave the protection of the atmosphere and the magnetosphere, then we deal with radiation. Some is cosmic radiation that originates outside the solar system, and some originates from the sun. There are two types of threats here, and one of them being gamma, just purely electromagnetic radiation. And as that comes in, it results in a gradual buildup of stress within the part that shifts the parameters of the individual transistors. And this can result in a state where the part could simply stop working. It can potentially go into latch up and draw high currents in a way that it could never recover because it could destroy the silicon on it. The other is ionizing particles coming in and can cause bit flips that will turn ones to zeros or zeros to ones. What Virago Technologies has is radiation hardening has two forms here. One, we take advantage of existing technologies that will prevent those bit flips from being able to corrupt anything going on. We have dice latches and triple mode redundancy on our registers, so that if when a radiation strike does come in and flip, this does happen, then, for example, on a TMR register, there are 3 copies, and the one that has been flipped will simply be outvoted. And in the end, the code needs to do nothing. It is just simply handled at the hardware level. And there's clock glitch filters on it. There is an EDAC and scrub engine to protect the memory, so any single bit flip inside of a word will not have any effect. The processor ultimately load the correct word, and it can correct errors. On the hard sill side, what is added at the mask level to the design is a buried guard ring that as TID comes in, starts varying charges in the part, which is what causes a shift in parameters that can eventually cause the part to become inoperative. It drains those off, and in the end, we get a 200 to 300 kRads of TID tolerance on it, and that is quite a high number. And we have a resistance for linear energy transfer from ionizing radiation for at 110 MeVs per centimeter squared per milligram at 125 C. We also have, as we are designed for the space market, we have ceramic packages that meet the outgassing requirements and the vibration and G-force requirements for space applications. And they operate across a very wide temperature range. Most people think of space as very cold, but in fact, as you are in a vacuum and exposed to sunlight, then in fact they can get very hot. And it is all and that's where our products are designed to address.
Okay, Danny, I had a question for you. Now, you were talking about some of the radiation threats. In terms of the severity of the radiation threat, could you talk a little bit about some of the differences between the equatorial orbits, low Earth orbit, geosynchronous orbit, and in between, and also talk a little bit about the radiation threat of polar orbits? And I ask that because I've read that, there's more and more talk about putting Earth observation satellites into polar orbits. I mean, what do you think of that?
Well, the polar orbits are a special case in that the magnetosphere can tend to route charged particles into that area. That's where we get the northern lights from, which are very beautiful, but not so good for satellites. That the protections here that hard sill offers are effective against these levels that should be encountered there. In low Earth orbit kind of gets a pass. It's largely within the protection of the magnetosphere, and we still wouldn't. It's still a great risk to COTS, to commercial off-the-shelf products, to try and employ them in electronics. That the space weather does change. While the cosmic radiation is fairly constant, anything coming from the sun and the way it interacts with the magnetosphere is highly variable. So we look for the worst case scenarios, and there's quite a large degree of variation in that. Once you go out to geosynchronous, which has a tremendous utility, it's for so many things, then the radiation level is much higher. It's outside the magnetosphere, and that is a problem. And of course, you go the moon has no magnetosphere to protect it. It doesn't have any atmosphere. There are special cases all over if you were to go to the poles of other planets, Saturn, Jupiter, then yeah, there's different radiation situations there.
Okay. Well, thanks, Danny. James, turning to you, I'd love to hear about the process the team went through when you started developing brushless controllers to meet the specific needs of space missions. What do you think about that?
Yes. So when FlightWorks started our motor controller effort, we recognized that there was a variety of approaches to how you can build it. And so as we went through the design process, we had to make a series of choices. One design dimension is do we want the product to be incorporate a microcontroller, or do we want to have a product built up of discrete digital and or analog electronics? We have seen off-the-shelf motor controllers that are radiation tolerant that appear to use the latter approach. This can work well, but fundamentally you're limited to the control algorithms that are already baked into the electronics design if you're using discrete digital and analog parts. At FlightWorks, we wanted the flexibility that a software-based algorithms can provide. So that pushed us towards a microcontroller-based platform. We also desired to offer additional products with even more functionality in the future, such as controlling additional pieces of a spacecraft, such as a small propulsion system. And so this also made a microcontroller appealing due to its ability to take on more functions. Another design dimension that Danny touched on as well is, low radiation tolerant parts versus higher radiation tolerant parts, and even truly extremely high rad hard parts. But focusing on the first two categories, we in CubeSats it is common to use non-space rated electronic components. As there are benefits there in cost, of course, if the radiation requirements can be met and if the risk tolerance is acceptable. These requirements, as Danny said, are certainly easier to meet in the low Earth orbit arena. In FlightWorks, we are interested in applications beyond LEO, like geosynchronous orbit and beyond. And so, with the inherent higher radiation environments there. One way to handle this is with non-space rated components is to add redundancy, but that can add a lot of complexity and can be very difficult to make reliable without a lot of design effort. Instead, FlightWorks' preferred approach is to use space-rated components that have inherent radiation tolerance and have very high reliability. Another dimension actually is the make versus buy decision. I mean, it's not really a design decision, but it's a project decision. We didn't find a product out there that met our customers' needs, which is why we started this project and to develop our own space-rated brushless motor controller.
Okay. Danny, can you tell us about the proprietary technology that Virago has developed to address the issue of radiation tolerance?
So that would be hard cell. That is a proprietary technology that Virago employs that can be. Currently, we produce a microcontroller, an M4, that uses hard cell. And that's the buried guard ring that its primary function is to take the TID, which would be the total ionizing dose from the gamma, and as those rays come in and embed themselves in silicon and create charges, the buried guard ring will simply drain it off without that charge biasing problem with the transistors that can ultimately result in dysfunction, latch up, and potentially destruction of the device. It will not happen up to, we have levels of 200 and 300 KRAD, which is an extremely high level of dosage, and we test that at a very high rate. The And it also operates off of a very robust temperature range.
Okay. James and Eric, what response have you gotten from your customers? What types of applications are they using your brushless controllers for today? And have they talked about any future applications they're looking at?
Maybe I'll jump in. This is Eric. So we started the program, as James alluded to, a little over a year ago, almost actually 2 years ago now. And so when we went from scratch to having a design, went through a couple iterations, and we've delivered already products that have gone, that are designed to go. They've not been launched yet, but their products are designed to go. So we've got customers for applications in low Earth orbit, where, as Danny mentioned, the environment is much more benign. We've got customers, one customer that's going to use those on the surface of the moon for a particular application there. And then the harsher environment, as Danny alluded to, is a geo customer, where it's going to actually be used in geosynchronous orbit. And actually even worse, in one of the applications that we're working on here at FlightWorks is something that actually is traveling between LEO and GEO, where you've got the Van Allen belts, and they're collecting much higher total ionizing dose there in that region. It's actually the worst place to be, and so you limit it very quickly, decrease the life of your space electronics if you do that. So we've got customers in all those regions, and as James said, we're really focused on being able to serve a high reliability product, high quality product, and it's certainly a lot more expensive than what people might do with COTS, and that can do low tens of K if you go and screen the parts and so on. Of K, I mean low tens of kilorad, that is. But it provides that next level of reliability, and then if you go to GEO, you can increase the actual thickness of material that you put around to give more resiliency, increase that even further than the 300 kilorad kind of thing that you can do typically on those kinds of on the product that we have, where we've integrated Virago's controller.
Okay, anyone else want to chime in on that? All right. Particularly James and Danny, I've got a question, and that is, it's not specific to this program, but when we're talking about radiation hardening for Earth and perhaps deep space and other planetary orbits, we're looking at new generations of systems on chip that might combine microprocessors, field programmable gate arrays, graphics processing units, all on the same system or all on the same chip. Do you see demand anytime in the future for this kind of advanced technologies for orbital type applications, and what do you see as some of the radiation hardening challenges for some of these advanced processor technologies? James, do you want to start with that?
Sorry, I was on mute. Danny might have more insight here in some of the aspects of the challenges, but I'll say, certainly you can. I think I should pass this off to Danny, actually.
Oh, that's all right. Danny, what do you think?
Well, I'd like to add that HardSill, while it is baked into our current products, in primarily the M4, is a general purpose technology. In any any design that is brought to us that would work in silicon can potentially be modified and fabricated with hard sill baked into it, and it could be given radiation immunity on that. So if customers are committed enough to go that route, we can bring the hard sill proprietary features to it and create a rad hard design out of some other part. So that could be an ASIC, potentially a motor controller could be built that way.
Okay. Well, this has been a great discussion. At this stage, I'd like to open it up to questions from our online audience. A few of you already have submitted questions. So we're going to jump right in. If you'd like to ask or submit a question, type your question into the Ask a Question box and hit the send button. Also, please take a moment to complete the feedback form that will appear on your screen at the end of the webinar. So our first question, it's for James. You talk quite a lot about brushless motor controllers. Can you explain in any more detail about brushless versus brushed motors and why that makes a difference in space missions?
Sure, yes. So some of the differences between brushless and brushed motors, brushed motors typically have a shorter lifetime, which is driven by the brushes. The brushes are used to commutate the motor, whereas in a brushless motor, the commutation is accomplished with controller electronics. And in addition, the reliability of the brushes is lower. The brush wear is more difficult to predict what its lifetime is going to be. So if you have a long life and high reliability application, a brushless motor is probably a better choice. And also, brushes have an even shorter lifetime if they aren't in an atmosphere. Having an atmosphere helps the brushes to function correctly. And if you're using graphite brushes, graphite dust is produced, which may also be a problem depending on the application. The brushes produce small sparks when they're operating, and that'll produce some amount of EMI, and that may or may not be a problem, again, depending on the requirements. Now, on the other hand, brushed motors are certainly a lot easier to drive, especially in applications where speed and torque don't need to be regulated. In some cases like that, you can run the motor open loop and just apply a voltage to it, and it turns at whatever speed and torque that it wants to produce. And so depending on the requirements, that can work well. In applications where you want closed loop control of speed and or torque, some kind of controller is necessary. And then the difference between the two is actually a little bit less, because the brushless motor needs a slightly more complex controller, but you've gone up a discrete step in complexity. You do need a controller. So yeah, those are the differences that come to mind.
Okay. Danny, you talked about radiation effects in space. Are there any specific considerations to take into account when deploying hardware in space? What do you think?
There are when we're talking about space applications. The first thing that's unusual, but that we don't normally think about, would be, so all materials have some degree of outgassing to them. It's the PC board material that gets used. And in our case, the packaging that would go that the die is in, once you're in a vacuum, you start outgassing things at it. And there's a great concern that that can affect other parts of the system. For example, CMOS image sensors, the optics on it can potentially be fogged by outgassing problems. So we have certifications on the plastic packaging, the sort of outgassing that they can do for our plastic parts. We have ceramic parts, which have no outgassing issues with them. We address concerns about the vibration and the G-forces involved in launch, which are completely different than the sort of things that we deal with in terrestrial applications. If we are going to use a BGA package, we pay particular attention to the type of solder balls that are placed on it and get the best performance possible for these vibration and G-force concerns. There is the wide temperature range that you can experience in a vacuum as you go in and out of the sunlight and the cycling. And we are familiar with space certifications that need to be done by various agencies, and in particular the export regulations that have to be followed. There are in the U.S. there are very strict rules on radiation tolerant hardware and how that can be transferred, and we can help you and make sure that process goes along smoothly.
Okay. James, which specific Virago part did you use and why is that part the best for this type of application?
Yes, we chose to use the Virago's VA 41630. This is a ARM-based, 32-bit ARM Cortex M4 processor. Some of the features that we liked about it were, of course, its high radiation tolerance. Both TID and single event latch up, which really to us really made it was a real differentiator. But in addition, the other functions that we used to choose this particular product out of Virago's catalog were its built-in analog to digital converter, which we use for monitoring some of the motor controller parameters like current and also temperature. It has timers on it that can produce PWM waveforms to drive the motor controller power electronics. Again, actually going back to the ARM Cortex M4, it's for an embedded microcontroller. It's reasonably powerful and can has a single precision floating point, which helps to make the control algorithms a bit easier to develop. And also out of the different products that Virago offers, this one has a non-volatile memory incorporated in the package, which overall reduces our part count because we can rely on that memory for storing our program and data that we need for the software.
Okay. Dan, I'm sorry. Did you have more to add?
Yeah, Eric, I was going to jump in here
Okay.
and make one comment related to what James just mentioned and what was discussed earlier in the context of brushless versus brushed. And one thing that we did, so when you do brushless commutation, usually people will use Hall sensors as well. So you have Hall sensors on the motor. They're going to feedback, give a position feedback and more of a position of action RPM feedback. And we can use that on the controller. And one of the challenges, again, looking at reliability, one of the challenges associated with Hall sensors, well, they're sensors, they're silicon-based, and they're going to be sensitive to the radiation environment as well. And so typically, decent reliability, space rated Hall sensors are going to be in the 30 kilorad range in terms of TID. And we felt, while we could use them, we actually implemented the harder, or James and his team implemented a harder version of the controller, and that was enabled by the microcontroller. We're doing this without Hall effect sensors, so we're not relying on the Hall effects to be able to detect the position or the speed at which the commutation is taking place. So using the back EMF instead. So there's additional math or computation that needs to take place to do that, and the microcontroller option really allows to do that. So you do the engineering on the front end with more development up front, but it gives you a superior product at the end of the day. So combination of things here.
Okay. I had a thought, a question for Danny primarily, I think, but Eric and James, if you'd like to chime in, and that is, when we're looking at orbital applications, a lot of people typically think in extremes. The one on the one extreme, we have the school bus size, exquisite satellite architectures that are operating in geosynchronous orbit, and on the other extreme, we have the so-called CubeSats that presumably are all COTS that are the size of a softball. Do you see a market established or emerging that's kind of more of a middle ground, something that maybe for commercial communications applications that might start from COTS but might require some level, perhaps some custom applications of radiation hardness? How do you see the markets emerging for something between the two extremes? Danny, what do you think?
Well, I must say the market's taken on a different character in the years that I've worked here. Initially, we thought of the market as very small. We get NASA, which launches a very limited number, but worldwide, we've had quite a few customers from that have emerged, and it's gone into the civilian market. Of course, is exploded, and these companies do have different degrees of risk tolerance concepts at it. The cost of launch has changed, and the risk assessment of having a single satellite fail when you can launch many at a time is definitely changed. But it always comes back to that it is most cost effective to have that your microcontroller itself, which is a very critical part of the system, is going to be able to continue to function. If sometimes if you look at it and say, okay, yeah, but the image sensor or some kind of graphics dealing on it, it has a problem. Maybe that can be dealt with as long as the central microcontroller continue to operate, continue to communicate and shut down, supervise things from there. So yeah, having a high reliability, radiation tolerant microcontroller at the core is always key.
Okay, James and Eric, do you have any thoughts?
I want to add that, for customers, in the lower end, as you mentioned, kind of COTS-based CubeSats, some of those are based off of ARM Cortex M4 processors that are just, a commercial part that you could, perhaps buy from DigiKey for $20 or something. But, one of the nice things about the Virago part is that it is also an ARM Cortex M4 processor. So many of the, kind of core features of the processor are the same. And, that I think helps to, ease the if you have a customer that is using a different part, it can help to ease the transition to using the Virago's microcontroller. Some of the peripherals are going to be different, but I think it can make the job a lot easier and help to reduce risk on the software side, which I think is often welcome on any software project.
Okay, Eric, do you have any thoughts?
Yeah, my comments will be more on the application side. You know, if you look at the, as you hinted when you asked the question, you have the bus size spacecraft, and then you had this what I call the small CubeSats, and like the size of a toaster, and that size is growing. The bottom size of those smaller satellites is going to grow, and is still growing. And right now it's in the couple 100 kilograms, where there's a lot of growth on the market, and it's probably, it's going to be somewhere in the couple 100 to 1,000 kilogram kind of range, where in the near future is going to be quite a bit of growth. And as a result, those are not, $100 or even a few K type spacecraft. So once you start getting to those points, you get to points from a market standpoint. Well, one is you need more reliability, and two is, paying $20 to, saving a few bucks by paying for $20 is going to increase or drastically decrease your reliability, is a bigger risk factor. And so if you can find a commercially viable radiation tolerant part, then it's going to make a lot more sense for usually a constellation or your application, whatever that might be. And so when you're looking at those particular larger buses, then that's where it makes sense to have that higher tolerance, higher decrease in sensitivity to the radiation environment, more something more readily available, and that's going to be increasing your reliability at the system level.
Okay. Well, I have one more question, and that is, why don't we start with Danny and then, move to James and Eric if you've got some thoughts. But, you mentioned that the commercial space market is exploding now. What is the one piece of advice that you would give to a relatively new company considering getting into the space market, based on the lessons learned and your mistakes and successes over the years? What's the most important piece of advice that you would give somebody? Danny, what do you think?
One thing I can think of there is something James touched on, is that as this is an M4 controller, it is following an existing standard. So we're not using special compilers or IDEs. You can work with Kyle, you can work with GCC, and simply bring in the header files and the programmer's guide and take off running and have a rad hard system from there. You could, if you wanted to, you could run this as an Arduino. There's not really a reason not to. It's all very accessible. We don't intend to be a company that makes special purpose compilers or anything like that. So it is very accessible to take an existing concept and at any point in the design stage, switch to a rad tolerant processor and work from there.
Okay. James, what's the one piece of advice you would give to people looking at the exploding space market?
I would say, it's great from a project standpoint to get to a functioning product as quickly as you can and iterate the design, I think nothing beats, testing your product, and if you let your program or project take too long to get to the point where you're actually doing development testing, then sometimes you don't find problems until it's can be very expensive to correct them. Kind of going along with kind of related to that a little bit is also, it can be challenging to manage lead times for space related parts. Sometimes their lead times are stretched out quite a bit. Actually compared to the lead times during the whole kind of COVID era, where there were significant supply chain issues even in the commercial side. Actually, I would say the lead times in the commercial side in the peak of the kind of COVID crisis were worse than the space side because the space side doesn't share some of the same pipelines, the manufacturing pipelines as microcontrollers that go into automobiles. Anyway, in any case, go through and identify your components early and work out what their lead times are. I think work with your suppliers to get always inquire about if there's samples or if there are if you can get one or two components early out of an order. Sometimes the vendors can might have one or two spare components that they can add into a batch or order, add into an existing manufacturing batch, or they might have on a shelf, which can help you by getting your product into testing earlier. And we've always been pleased actually with Virago's performance in terms of lead time, delivering reliably, and those kinds of things.
Okay, Eric, what's your best piece of advice for someone interested in the commercial space market?
I think I'll try to complement what both Danny and James mentioned and emphasize what they said, or build on it in a way. If somebody trying to do it on the commercial side is hopefully going to look at it, and I would assume it's a technical audience, so it's probably going to be looking at it from a technical standpoint, have something unique, right? And so what you want the person to do, whoever you are, whatever it is, product or new technology that you're working on, you want that new thing to be what's going to be the differentiator in your product. And you want to build on it quickly, get to it as fast as you can. And so what that means is where there are technical solutions where people have done the homework, people have done and gone through that development, they've matured the technology, they've shown that it works. Just take it and build on it for what matters to you, what's going to make your product different. And so in that context, that's what we tried to do here. Look at where the technology was for, we wanted that digital microcontroller. How do we get there quickly? What are the best products that we thought were out there for being able to build on them and integrate them for the product we wanted to do as quickly as we could, so we could deliver for the customers that we had in a fairly short timeline. If you think less than a year from project start to delivery of the first flight hardware, that's pretty challenging in the space business, but that's what we were able to do by taking on that approach.
All right. Okay. Well, that's our presentation for today. So on behalf of Military and Aerospace Electronics, I'd like to thank James and Eric, along with Danny and Jim, for an excellent discussion, Virago for sponsoring today's event, and of course, all of you for joining. So I'm John Keller, Chief Editor of Military and Aerospace Electronics.